Good afternoon, everybody. Thank you for joining me on this snowy afternoon. So we've got our last sort of regular normal lecture of the semester here. We're just going to review for exam 4, whatever you want to talk about. So we have a special guest, my daughter. She is joining us because there's no school today. So, but I think she's going to be just fine over there. So hopefully be quiet. Enjoy your tablet. All right. Where do you want to start? I have one of the exams up here. This is exam 4 from 2024. I could dig into that one, or I could go into the other one, or, you know, we don't have to go through things linearly if you don't want to. What's on your mind? Do you have any questions that you want to crunch through, or should we just kind of like work through it? Okay, let's see what's in here. Okay, so this is 2024. Molecules of the day will be different, so we don't need to work on that one. Here's an aldol question. It's asking you to draw the structures in the boxes to complete the aldol and dehydration reaction sequence below. So this is one where you're given an aldol product and you're asked to figure out what aldehyde or ketone would you need to put in along with sodium hydroxide to get this aldol reaction to go. So that involves forming an enolate anion. So aldehyde or ketone reacts with the base, gets deprotonated, forms an enolate. So, and then that enolate reacts with another molecule of that same aldehyde or ketone. So let's see here what we can do with this one. The key is recognize the alpha and the beta position. So I'm going to zoom in on this. There's an alpha position and there's a beta position, and the aldol reaction occurs between alpha and beta. So that's the bond that forms. The two pieces are the things on the left part of the squiggle and the things on the right side of the squiggle. So, so really, this bit over here represents the molecule, and this bit over here is the same molecule. It's just that this one has had its carbonyl attacked by an enolate at that position. So, going back to this one, it's pretty simple. You can just go like this and say, here is my ketone. And this is the alpha position. It ends up becoming an enolate anion. It gets deprotonated there by the base. And then it attacks another molecule of the ketone. And I'll draw that other molecule, the ketone, over here in a way that suggests how it could go together. So like, for example, like right there, basically. And so you can imagine if you make an anion here by deprotonating, then that's a nucleophile. It attacks here, and that's how you get the carbon-carbon bond. And then electrons go up into oxygen. That O- gets a proton from water, and you have this aldol product. Then there's a dehydration reaction that happens. And so the thing about that you got to remember is that the dehydration happens between the alpha and the beta positions. So we're going to be losing water to make a double bond here. There's a proton there, and that's important. There has to be a proton there in order for this dehydration reaction to work. And so what happens is a base grabs that proton. I'll just draw OH- here to show you how this works. Grabs that proton, these electrons swing in like this, OH ends up leaving, and you end up with this molecule that's got a new carbon-carbon double bond between the alpha and the beta positions. And there's the water. So you can, as long as you keep track of where the alpha position is and the beta position is, usually that's the key to getting these aldol reactions correct. It's just got to get the double bond in the right spot, got to connect the two carbonyl compounds together in the right spots to get the aldol product. Any questions on this one, though? Okay, that's good aldol practice. Let's see what else we've got here. This one is about forming an enolate. So it says, draw both resonance structures of the enolate that forms in the following reaction. So that's part A, and then part B says this aldehyde and enolate can react to give an aldol product. Can this aldol product undergo dehydration? Well, let's get the enolate first, and then we can talk about that. So enolates form when the alpha position gets deprotonated by a base. So there's the alpha position. It's the position next to the carbonyl. There's got to be at least one H there to pluck off to form an enolate, and there is one. So the hydroxide is going to grab that proton. So here it goes. I'll draw several lone pairs on this. Away it goes. These electrons go to the alpha position, and that gives an enolate. And this is the enolate in one of its two resonance structure forms. This has got minus charge on that alpha position. I'll put alpha there. And there it is. So there's a lot of negative character at the carbon, but that's not the only resonance structure. And to get the next one, what you need to do is share the electrons differently so that the minus charge gets shared with the oxygen. So the stuff I'm drawing in blue here is not required for this answer. It's just kind of like information that might help you get there. And there is where the alpha position was. So those are the two resonance structures. Between the two of them, this one is a more stable resonance structure. It looks a bit more like this one than it does like that one. But when it reacts in an aldol reaction, that alpha position is the one that attacks the carbonyl. So this is the nature of enolates, is they have two negatively charged atoms, but that's the one that leads to an aldol product when that one attacks. Any questions about this one? All right, well then the next question, let's deal with this next one here. It asks, this aldehyde and enolate can react to give an aldol product. Can that aldol product undergo a dehydration reaction? The answer is no. And the reason is it doesn't have enough alpha protons. So I'll just sketch out the aldol product that comes out of this reaction so we can see that maybe. So here's the aldol product. When this aldehyde does an aldol reaction, you get this. There's the alpha position right there. There aren't any protons on that position. So it can undergo a dehydration reaction because there's no alpha H to abstract, which is what you need if you want to make a double bond between these two carbons. You got to pluck a proton off to make that bond. And so this one can't dehydrate. So the general thing is to form an enolate, you need at least one H in an alpha position. To then undergo a dehydration reaction, aldol and dehydration reaction, you need at least two. So there's a answer for that one. Questions about that one, or is that one pretty good? All right, let's talk about reactivity. Rank the following carboxylic acid derivatives in order of reactivity with nucleophiles, where 4 is most reactive and 1 is least reactive. So you got to write a number 1 through 4 below each. So it's got to do with how good the leaving groups are in these cases. So chloride is the best leaving group of all of them. I'll just circle the things we're looking at here. So among the leaving groups, these are the ones we're looking at. Chloride is the best leaving group, Cl- because it's the weakest base. So if you imagine a nucleophile attacking carbonyl and leaving group leaving, you get a Cl-, or you get a nitrogen-, or you get an OCH3 where the O has a minus, or you get an O carbonyl CH3 where that O has a minus and it's resonance stabilized. So the chloride, because it's the weakest base, is the best leaving group. That makes this the most reactive. So this is going to get the 4. Behind that is the anhydride. Anhydrides are a little less reactive than acid chlorides, but they're still really quite reactive because the O- that you get here is resonance stabilized between 2 oxygens. So that's still pretty reactive. It's still really a good leaving group. Oxygen that is on in this molecule in the ester, when this leaves, it leaves an O- that's not resonance stabilized. So that's a lot more basic. It's a lot worse leaving group. It's a lot less reactive. And then the nitrogen is the worst because nitrogen leaves as a very strong base. Oxygen is a better place for a minus charge than a nitrogen. I know that from this periodic table because the electronegativity difference. Because oxygen is further to the right, it's more electronegative, it handles negative charge better. So O- is a weaker base than nitrogen. Nitrogen- is a way stronger base. So N- is strongest base, worst leaving group, least reactive. O minus that's not resonance stabilized is a little better, a little more reactive. And there we go. Unless you have questions about it. Okay, well, let's push on. Complete the Fischer esterification reaction below by drawing the neutral tetrahedral intermediate and the ester product. Okay, so what happens in the Fischer esterification reaction is that these, let's see, the OH on the carboxylic acid ends up getting that hydrogen that's on the alcohol, and they leave as water. And so that's, in the end, what you end up getting. The way the mechanism works is there's a whole bunch of steps, but it involves acid protonating carbonyl, oxygen attacking here, and then conjugate base grabbing that proton back. So what the neutral tetrahedral intermediate ends up looking like is there is a intermediate, there's two OHs, and then this O looks like that. So this carbon right here, that used to be the carbonyl carbon. And the alcohol, you can see most of the alcohol here. One of the H's that's on these two oxygens, one of those came from the alcohol. So that's the neutral tetrahedral intermediate. Then what happens in the second half of the mechanism is that the strong acid protonates one of these OH groups to make it into a good leaving group, then it leaves. And then you get the full ester. And so that ester looks like this, where it's got carbonyl attached to the OR group. There it is. Any questions about that? Fischer esterification reactions can go the other way too. So if you have an ester and you put in excess water, like you put this in with a whole lot of this in with ester, you can go backwards through the mechanism and generate from an ester carboxylic acid and alcohol. All right. Oh, it's a bunch of complete the reactions, draw the reactants or the products. And it looks like the thing in the middle is an acid chloride. So this is where we're going to start paying attention. We have to figure out what we need to put in here with SOCl2 to get this acid chloride, and then the acid chloride does some reactions. So you can approach this one in whatever order you want, whether you want to work on this part first or this part first. It's kind of up to you. Let's do this one first. So acid chlorides, we learned one way to make those, and that's you use this thionyl chloride reagent with a carboxylic acid. So the thing you need over here is carboxylic acid. So you just put in the carboxylic acid. It's got the same carbon skeleton. It just has an OH here, and then the thionyl chloride activates the OH, makes it into a good leaving group, and then Cl minus attacks here and displaces it. And then you have acid chloride. And then this one is probably one of the harder parts about this. It's saying to get this product, you add water to something, and then you get a big hint here. The structure is an anhydride. So this is anhydride hydrolysis. So if you put an anhydride in with water, you get carboxylic acid. So the way this works is it's just an anhydride that has two carbonyls in it and the same R group on either side. So the anhydride for this reaction would look like this. It's got the two carbonyls, and then on both sides there's isopropyl group. And so when you add water to that, you generate two equivalents of that carboxylic acid. All right, then it's time to figure out what does the acid chloride do when it reacts with these things. So this is acid chloride reacting with alcohol. That's going to make an ester. And then this is pyridine. That's a weak base. So this one wants you to put two products in here, one neutral and one salt. So that's going to be like, what's the ester look like? And then what happens to this thing? So ultimately what happens is the alcohol attacks the acid chloride leaves, and then the pyridine lone pair on that nitrogen grabs that H. There's multiple steps to this process, so it doesn't like happen you know, quite that simply, but that's the end result. So what you end up getting is an ester where we have an OCH3, and that's the new bond that we made right there. And then the pyridine, this weak base, has got a proton. So the pyridine bit looks like this. It's got nitrogen with proton and formal plus charge, and then there's a Cl minus that came from the acid chloride. So that's the complete picture of what happens. Sometimes you're asked about this product, sometimes not. So it just kind of depends on the nature of the question. The ester is the more interesting product, but once in a while, you know, like Alex or a homework question or an exam question might want to see if you know about this one as well. Okay. Very similar kind of question here. This is reaction of the acid chloride with two equivalents of amine. So the amine is also a nucleophile like the alcohol was. It's even better nucleophile. There's two equivalents because one equivalent is needed to act as a nucleophile, and then another equivalent is a base that grabs a proton and gives a neutral amide. So the product here is, get the amide, the OCH, the CH3 on here, it's neutral. The bond that was made was right there. And then the fate of the other equivalent of amine is it ends up being this conjugate acid. It's gotten the proton off of the first nitrogen. So that's the second product. It's a salt. One neutral, one salt. That's the salt, and then the neutral is the amide species. So, yeah. Questions on that one? All right, let's look and see what's next. All right, the molecule N-acetyl carnosine is used in eye drops to treat cataracts. It contains two bonds that hydrolyze with either aqueous acid or aqueous base. Draw wavy lines through the bonds that would break during hydrolysis. So this is all about trying to figure out if you put in water and either strong acid or strong base, where would it break? So we just have to figure out where all of the derivative type bonds are, like because amides and esters become carboxylic acids, and we've got an amide here. We have an amide here, and we don't have any esters in this molecule. But one of the amide bonds is right here. It's the bond between the carbonyl and the nitrogen. So if you put in water and either strong acid or strong base, it would break there, and the OH would be attached to that carbonyl, and the piece on the left side of the squiggle would float away as a separate molecule. Then we've also got one of these amide bonds over here. That would also break. So those are the two spots. Those are the two weak links in this molecule. Between the carbonyl and the heteroatom. All right. This is one that we didn't talk about, so you won't see polymer questions on this exam. Not at least from the new material that we talked about. We talked about polymers before on exam 3, so that's, or was it exam 2? Chapter 15, where we did that one. I think that was exam 2, actually. Yeah, it was exam 2. But this is one where it's a polyester type material. So it wants to know if you were to depolymerize, or if you were going to polymerize this, what species would you need? What I'm going to say about this one is just keep it really simple, and just highlight that there are some ester bonds in this thing. There's an ester bond right here. And so just like above, the place where this is would break would be there, and there's another ester bond there. So those are the positions between the oxygen and the carbonyl. Those ester bonds would either break in hydrolysis or form when you make an ester. So, but don't worry too much about this one because we didn't talk about that stuff this semester. All right, here's an ester, and it's reacting in two different ways. There is, on the arrow to the right, an amine, and esters can get converted to amides because amides are less reactive than esters. So this is an aminolysis reaction. And what happens is the nitrogen acts like a nucleophile and attacks, and the leaving group leaves. And there's more steps than that, but this at least gives you conceptually like what's going on. I gotta wake up my computer. There we go. So you get an amide out, and here's what that amide looks like. You get NH2, and the fate of the OCH2CH3 is it ends up as an alcohol. So that's that other product given to you to kind of give you a hint and make the problem a little easier. Right? This direction, going from the middle to the left, it's sodium hydroxide. This is a saponification reaction. So this is OH minus really strong base attacking carbonyl and breaking it. And in both cases, it's that bond right there that breaks. So here, it's just a different nucleophile doing the attacking. But the same thing happens. You lose that ester bond and you make a different bond. In this case, we're making carboxylic acid. So our product would look like this. O minus, there'd be a sodium plus, and the alcohol. Now, if you put down the carboxylic acid here, you'd still get most of the credit for it because carboxylic acid is just a protonated form of the actual product. But if you're using sodium hydroxide, that's really strong base, the carboxylic acid would not be protonated, it'd be deprotonated. So it would be that salt. And then there's the alcohol leaving group that left. All right. And that is the end of the like new stuff from this exam from last year. Then it went on to the comprehensive part of the exam, which is, you can kind of tell the shift in tone. Now all of a sudden we're on mass spectrometry, which was the first thing we talked about this semester. So this is a question about mass spec, and it says the mass spectrum of tert butyl alcohol gives a base peak at 59 that results from alpha cleavage. Draw one resonance structure for the base peak. So let's figure out, look at this thing as far as alpha cleavage goes, try to figure out what happens in the alpha cleavage process. So for alpha cleavage, you first generate a molecular ion, which is what this thing is. I can tell this is a molecular ion because it's got all the atoms in it. It has a positive charge and it has a dot. So this is the molecule, tert butyl alcohol, that's just lost one electron. So this is the molecular ion, the M plus dot. And then to figure out what happens with alpha cleavage, you look at where the heteroatom is, which is the oxygen, and what it's attached to, label that alpha. So I'll put a little alpha label on that. And then the next door carbon would be beta. And there's 3 identical beta positions here, methyl, methyl, methyl. You could use any one of them you want. I'll just pick on this one here and I'll call that one beta. But the other methyls would be identical beta positions. And so when alpha cleavage happens, you break the bond between the alpha and the beta position. So one of the pieces that's going to leave here is going to be a CH3, and we're going to lose that as a CH3 dot. And you're not asked about that one. You're asked about the other peak. So I'll just draw off to the side here a CH3 dot. And then what you get on this other position is the electrons in this bond, it breaks homolytically. So one electron goes to the CH3, that gives you a CH3 dot. The other electron in that bond pairs up with that dot, and that'll give you one of the 2 resonance structures. So I'll show you like from an electron pushing perspective how this works. I'm going to take one of those electrons and give it to the beta carbon to make the CH3 dot. So that CH3 dot that I drew over here, that dot came from one of the electrons in that bond. The other electron in that bond, I'm going to push it in here and pair it up with this electron, and we're going to make a new carbon-oxygen double bond here. So that's going to be one of our two resonance structures. So I'll take this, blow it up a little bit, and draw one of those two. And you were only required to draw one of them here, so this would be all you'd have to do. The result is there's one lone pair left, formal positive charge on the oxygen. There's a couple of methyl groups that are still attached that have not gone away. So that's one of them. That weighs 59. And then if you wanted to, you could draw the other resonance structure, alternately. So the way that works is you take a pair of electrons, share them differently by giving them to oxygen. That gives a resonance structure that looks like this, where there's the positive charge is now on the carbon. Either one of these resonance structures is fine. The one that's up above is more important. This one is a more stable resonance structure because all the atoms have octets. So, if you're going to draw the most stable one, it'd be this. But this one is also fine for this question. So that's alpha cleavage. Right? It's just remember, look for the heteroatom in your molecular ion. Look, the carbon attaches alpha, the next carbon's beta, break it between alpha and beta. All right. A couple of multiple choice questions here. Decide whether each of the following properties affects frequency or intensity of peaks in IR spectroscopy, and you circle one option for either one. So, so mass of atoms. So if you've got a bond and vibration of that bond is resulting in a peak, the bond vibration frequency depends on how heavy the atoms are. In other words, if they're really big and heavy, the frequency will be low because they're slow. They're big and slow atoms, and they change direction with a lot of difficulty just because they weigh a lot. Big things aren't all that nimble, don't change direction all that fast. So mass of atoms affects frequency, but not intensity. Intensity is how big is the peak. They don't do that. They affect frequency. Bond strength, that's another one that if you're talking about the frequency, like how fast does it vibrate? How fast do the atoms move back and forth? Bond strength makes a big difference here because strong springs vibrate quickly. They're stiffer. If you've got a weaker bond, think of that as a weaker spring, and think about if you stretch that and let it go, it would vibrate, but it would vibrate at a lower frequency. So frequency is also, for this one, bond polarity. That's like if you've got the two atoms that are vibrating. If there's a partial positive on one and a partial negative on the other, that really helps. And the bigger those charges are, the easier it is for the electromagnetic radiation, IR radiation, to sort of tug on that bond and vibrate it. So I usually like to think of carbonyls as my go-to example for this. The carbonyl is a really polar bond. So C double bond O has a big partial minus and a big partial, or big partial minus, big partial positive. So when you stretch that bond, you make those differences in charges bigger. You pull those charges apart. You generate more charge separation. And this is usually the strongest, most intense peak in a spectrum. So this is a very strong peak because it's a very polar bond. There's a big difference in atoms. Other double bonds that don't have that big a dipole, they generally have weaker absorptions, like carbon-carbon double bonds. They tend to be much weaker. So this is one where it affects frequency, not frequency, intensity of the peak. You get big peaks when you have polar bonds. You get small peaks when you have nonpolar bonds or weakly polar bonds. All right, now we're moving on to NMR spectroscopy. Here's a molecule. How many unique types of protons are there in this molecule? And if you need to, or if it would help you, you can build models of these things. You're going to want to look for symmetry. And at first glance, it might be a little hard to figure out where is the symmetry in this molecule, but I'll draw it in a way that maybe makes it a little easier to see. There's a mirror plane of symmetry in this molecule. If I redraw it like this, maybe makes it a little easier to see. And the thing about the symmetry that's important is that if you can find an internal mirror plane of symmetry in a molecule, like a way to bisect it exactly in half, so that one half is the reflection of the other half, then the reflecting protons are the same. So if we look at this molecule, these CH3s, they are reflections of each other. That's one type. And the CH3s on any given carbon on a methyl are always the same. So those 3 H's are the same as each other. Those 3 H's are the same as each other. And since there is a mirror plane here, those CH3s and those CH3s are the same. So I'll give that a label. I'll call that A. And those are also A. The proton here is all by itself the only type that's like that. It's on a carbon that's attached to 2 methyl groups. Tertiary carbon, tertiary hydrogen. There's no other one like that. I'll call that one B, just to distinguish it from A. Then we got a couple of CH2s. There's a CH2 here. These 2 H's are reflections of each other. They're the same as each other. I'll call those C. And then we have another CH2. These H's are the same as each other, but they're not the same as this CH2 because they have different proximities to this oxygen and different proximities to this isopropyl group. The H's that are on this carbon are close to the hydrogen and are very affected by it. That OH, that oxygen, pulls a lot of electron density away from it. These H's are in a much more electron poor environment, so they're different. They would be D as in dog. I'll put the label D on there. And then the proton on the oxygen is also really, uniquely different. Yes. Oh, it's a Cl. I'm sorry. How did I do that wrong? Yeah. All right. Well, then we can erase that. That makes it a little simpler. Thank you. Oh no, that's weird. Why was I doing that? All right. Okay. Erase. Thanks for the catch. You'd be like, what's going on? So A, B, C, D, 4 proton types. You can do the same trick with carbons. Just look for mirror planes of symmetry and count. Methyl carbons are one type. That's another carbon type. That's another one, and that's another one. So we've got 1, 2, 3, 4. So the answer for the carbon types is also 4. They don't necessarily always agree with each other, so be careful. Sometimes there are more unique protons than carbons. Sometimes there's more unique carbons than protons. It really is molecule dependent. So you just have to look at every single one and not try to guess at that. Okay, any questions about that one? All right, what is the NMR multiplicity or splitting for the signals indicated by the dotted rectangle? So these H's right here, what we need to do is figure out how many neighbors do they have. They don't split each other, but if you look next door, and I'll highlight the next door carbon or atoms. Actually, what I'll do is I'll highlight all the atoms that are within 3 bonds. There and there. Okay. All right. What we're doing is we're looking for protons that are in the right vicinity. So they got to be within 3 bonds. So here, if you count the bonds, 1, 2, 3, 1, 2, 3, and then 1, 2, 3, those work. But over here on these, that'd be 1, 2, 3, 4. So none of these count as neighbors. So I just counted 3 neighbors, and then to figure out the splitting, you take the number of neighbors and you add 1. That's that n plus 1 rule. So n plus 1 is equal to 3 plus 1 is equal to 4. So 4 is quartet. They also, in order to split, they have to be different too. So one of the things you have to look at is, are these H's actually different than these two? In this case, they are, because these H's are next to a methyl. These H's are not next to a methyl. They're next to isopropyl and an ethyl. So they're different, and that's a difference that means they're going to split. All right, now we got an unknown problem. These aren't really all that hard, but you don't have like a lot of space and a lot of structural information here. So let's work through this one and just give you some pointers about how I would go about doing this one. We're told the formula is C6H814O. If you've got a formula, work the degrees of unsaturation equation, just because why not? I mean, that tells you whether you should be looking for a double bond or not. So let's calculate degrees of unsaturation. Degrees of unsaturation is equal to 2 times the number of carbons minus the number of hydrogens minus the number of halogens if there are any, plus the number of nitrogens plus 2, all divided by 2. And that formula will be on the exam, so you don't have to remember it. You just have to know how to apply it. So in our molecule here, we have 6 carbons. So we've got 2 times 6. And then the number of hydrogens we have are 14. We don't have any halogens. We don't have any nitrogens. We have the 2 that we add. And oxygens you just ignore for the purposes of this formula. Sulfur also, you just ignore it. So we get 12 minus 14, which is minus 2, plus 2 is 0, divided by 2 is equal to 0. So what that means is there's no pi bond, there's no ring. So we're looking for a saturated species here. There are only 2 signals in the proton NMR, and this one is a doublet for 12 protons. Oh my goodness, that's a lot of protons. And then we've got a septet for 2 protons. Let's think about this septet, because that's an interesting one. So to get a septet, what you need a proton that has 6 neighbors. I think what I'm going to do is just draw this just a little bit differently. I know I have a proton and it's a septet. That's telling me it's got 6 neighbors. And I know that because the n+1 rule says if I have 6 neighbors, add 1 to it, I get 7. So somehow I have to get 6 protons next to this one. One way to do that would be to have 2 identical methyl groups. So that would give you a septet. It would be area 1, but it would be a septet, and then we'd have 6 protons accounted for here. And the thing about this one is that that's all you get. This is from the NMR spectrum. This is the only signals we have, and it accounts for exactly half of the protons. So what you want to think about when you have a proton NMR spectrum and you're struggling to come up with enough atoms. We've accounted for 7 atoms here. We know we have 14. Is symmetry is maybe there's 2 of a particular group. So if you just double this thing and put another one of these on the other side, there's a mirror plane of symmetry here. That one and that one don't split each other because they're the same type of proton. So you don't get splitting here. Basically the fact that there's these protons, there's 6 here and there's 6 here, add them together, you get 12. There's a proton here and a proton here, add them together, you get 2. So that's how you get the thing to work out. It's a high symmetry molecule. Isn't there oxygen in there? Oh, you know what? There must be. Good catch. Yes. Okay. Ha 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 ha. Yeah. Good. Yeah. Don't forget about the molecular formula. There's an oxygen in there. Thank you. So where would you put the oxygen? Well, yeah, okay, good, because you don't want to break the symmetry. If you stuck it here, you wouldn't have a symmetrical molecule anymore. So yeah, just jam it in the middle. There you go, right there. Good. We still have our mirror plane of symmetry. We still have our 2 identical isopropyl groups. Yeah, thank you. That fixes the problem. Awesome. Okay, let's look at this next one here. All right, so this is a question that wants to know about a bunch of reactions, oxidation reduction reactions. This is stuff from chapter 12. When you get to this one, you should really break out that sheet that has all the reactions from chapter 12. I'm gonna go here and see if I have it included in here. Oh, I bet I do. Yeah, here we go. Remember this one? All right, it's got a whole bunch of different oxidizing and reducing reagents. So you can take this off the back. It'll be on the back of the exam. You can tear it out and look at it, or flip back and forth, whatever works for you. Okay, so just to point that out, we've got a whole bunch of reagents over here. Let's see what our reagents are. We are doing a sodium and ammonia reduction, and that it's giving us a transalkene. This is a reaction that takes an alkyne as a substrate. In other words, a carbon-carbon triple bond. So these conditions produce transalkenes from an alkyne. So we just need to find the molecule that's got methyl groups on the end of a triple bond. So that would be A. Then when you put an alkene in with a peroxy acid, and this is in the list as well, you make an epoxide out of it. And so we just need to find the epoxide from the list here. And oh, there's two epoxides. What do you do here? Well, it is a transalkene. Transalkenes give trans epoxides, because that's one of the rules that we learned. So between these two, that's a cis epoxide. That one isn't one I would select. It's E. So E is the answer here. Oh, everything okay over there? All right, sorry. This is kind of a big experiment, seeing how this is going to go. I'm really hoping it's good, but okay, we got ozonolysis here next. O3, and then SCH3, two of them, disulfide, dimethyl sulfide. This clips double bonds right down the middle and makes aldehydes out of them. So we got to find the thing that's aldehyde. So when you clip this one, you get an aldehyde with a CH3 and another aldehyde with a CH3, because they're the same. So that structure is B. And then finally, we're taking an alkene and we're putting hydrogen, palladium on carbon with it. So we're adding hydrogen across the carbon-carbon double bond. That's going to give us D. Again, this is one. The key is just get that table out and look for it. All right. Here's one that's a chlorination reaction. It's a free radical chlorination of an alkane. So with this one, we got to figure out where all the unique places we could put one chlorine here. So you could put it on the methyl, and that would give this one. And this is an achiral molecule, so there's no stereoisomer here. Even though there's a dash and a wedge, you draw a mirror plane of symmetry through this molecule like this, and it's not different. If you have the chlorine on the top carbon, it's the same. So that's one of them. Then we've got H's on these carbons. The thing about this one, I want to maybe point this out before we even get started with this, is there's this mirror plane of symmetry that do this a little better. Mirror plane of symmetry that cuts through the molecule right there. So if you put a chlorine here or here, it's the same. There are two H's on each of these carbons. There's an up-pointing H and a down-pointing H. If you do one of those, let's see what we get. Like this one results from taking one of the up hydrogen and replacing with a chlorine. There's that one. And then over here, since that lies on the mirror plane, taking an H off of either the top or bottom will give you the same product. So this one is the same as the one where the chlorine is pointing down, because they're just rotational forms of each other. This one, though, there's a stereoisomer of this one that we would need to draw, and that's the one that's missing, and that's the one that you need to draw. You don't need to show stereochemistry on the methyl groups unless you want to. But since it's not a stereogenic center, you're not required to do it. But here you need a dash bond to indicate that that's the stereoisomer of this one. These are each chiral molecules, and they're non-superimposable mirror images. So that's the one that's missing. All right, on to allylic bromination. which structure is not a possible product in the allylic bromination reaction shown below? So let's identify allylic positions in this molecule. We got one here, and we got one here. And there are H's on each of these spots. There's an H here that's an allylic H. And there's a couple of H's here that are allylic H's. So we could put a bromine here or here. That's definitely true. So let's take a look at those. A comes from if this H were replaced by a bromine. B comes from if one of these H's was replaced by a bromine. There's a couple of resonance structures that we need to look at too, because you put a dot in one of those highlighted positions, it has a resonance structure. So let me draw maybe those resonance structures for you. So one of those is, okay, if we pluck off this H, puts a dot here, then you can draw a resonance structure where you put the dot over there. That's one of them. And if that were to grab a BR, that's exactly like E. All right, then the other possible resonance structure is if you were to pluck one of these H's off, you make a dot here, then there's a resonance structure where you get a double bond here and a dot there. Let's draw that one. Just over off here on the margins. This might be one where it'd be good to get a piece of scratch paper and work on it, just because it's, you know, there's a bit of stuff to keep in your head. But if you look at this, C is the bromide that could come out of that. So the one that is left over that we didn't find a way to make is D. That one just isn't, there's just no way you can get there, because the H way over here on this methyl is just too far away. It's not an H that could get plucked off in an allylic bromination reaction. So the one that doesn't make sense is this one. All right. Diels-Alder reaction. What you should do with these, if you've haven't gotten kind of used to it already, is draw it in the Diels-Alder transition state. So identify the diene and the dienophile. Draw the diene in the S-cis conformation, which is the one you need, and then put the dienophile next to it to form the six-membered ring transition state. Push electrons around in a circle and draw the product. Or products, we'll see what we get out of this. You need to show for sure the stereochemistry of the product. Now this is a product that doesn't have any stereochemistry shown, but we know that since it's a cis dienophile, the product has to be cis. So we need some indication of that, and one way you could do that is to show a couple of wedges here. That's one product. That's a cis product, but it's one of two possible stereoisomers. The other possible stereoisomer is this one I'm drawing right now, which has dashes instead of wedges. So those are the two Diels-Alder products that you would need. And the directions are even pointing to this. It's saying if stereoisomers form, draw them both. All right, the next one wants to know, draw the missing dienophile to complete the following Diels-Alder reaction. So we've got this diene with a bridging group here. So I think what I'm going to do, just to kind of help point out what's going on here, is these are the atoms in the starting diene. I'm going to highlight those in the product. There they are. The new bonds that we're making are there and there. So this piece right here, this is our dienophile. That's the piece we need to have be the dienophile. And the double bond is going to have to be between these two carbons. If you want to work that backwards, one way you can do it is if you push arrows in the other direction. One thing you could do is you could take the electrons out of one of these bonds, push them this way, and then these electrons go this way, and these electrons would go like that. So we're going to end up with a carbon-carbon double bond that's got an ester group on one end, OCH3, and an ester group on the other end, right there. And you got to show this as being trans, because this product is trans. That methyl group is pointing towards the top of the page, and this ester group is pointing towards the bottom. And one more thing, there is a methyl group here. There. If you were asked, what are the groups that are endo? You're not in this case, but it's this ester is in the endo position. That H is also in an endo position. And then that methyl and that ester are in exo positions. Just a sort of a little aside in case you're wondering about that. All right, aromatic rings. Would the following molecule be more stable in a flat or puckered conformation? So this is a ring that is fully conjugated when it's flat. It has sp2 hybridized atoms all around, an unbroken ring of p orbitals, and if you flatten it out, it's either going to become aromatic or anti-aromatic. We just have to figure out which by counting the number of pi electrons and see if it fits the 4n plus 2 rule or 4n type rule. So let's just count, and what I'll do is I'll just put a little mark here to count to mark. I'm going to start counting here. And I'm going to start there. I'm going to go 2, 4, 6, 8, 10, 12, 14, 16. So 16 pi electrons. That is a 4n type system. It's anti-aromatic if flat, which is a bad way to be. So it's going to want to avoid being flat at all costs. So it's going to want to pucker. So puckered is more stable. More stable for this molecule because of its arrangement of pi electrons. Then this one gives a molecule that's got a couple of nitrogens in it. Is the following molecule aromatic, anti-aromatic, or non-aromatic? Assume the molecule is flat. So this is one that's just telling you, hey, it's flat. Tell me about if it's aromatic or not. So if you look at it, every single atom in this ring system is sp2 hybridized. Every single atom has a p orbital on it. That one is sp2 hybridized because it's got an XYZ type system going on, and that one is sp2 hybridized because it's making this double bond with the neighboring carbon there. So we've got to figure out which of these are pi electrons. So we've got every pi bond is pi electrons, so we get 2, 4, 6, 8. And then what you need to know is what's going on with these lone pairs. The one here, because that's on a nitrogen that's inside the ring and it's part of this XYZ system, these are pi electrons. These are pi electrons. They count in the total. These are in an sp2 orbital, not pi electrons. So you don't count those. So when we're counting up electrons, we've got the 2, 4, 6, 8 from the double bonds, and then we count that as 10, but we don't count those. So this one has 10 pi electrons in its ring system. 10 pi electrons total. That is a 4n plus 2 system. That's one that is going to lead to an aromatic ring. So yeah, that's a real molecule that turns up in a bunch of places. All right, draw the missing products to balance the following equation. So this is a simple acid-base reaction. We've got an acidic proton here, and we got a strong base here. Oh, yes, question.
Did you circle the tetramer pair that's basic?
Let me go back here. This is, so the question is about this molecule here. The one that's got the sp2 hybridized orbital, these are basic. This question doesn't ask about these, but this is a good thing to put down as just sort of an aside. These lone pairs here, these are not basic. Because these are required for making the ring aromatic, so they're not available for sharing. It's a good question. All right, here we've got a base and an acid. Carboxylic acids are acidic. So what comes out of this is a carboxylate salt. And the sodium is the counter ion. And then we also get an H2O water. That's the conjugate acid of the hydroxide. All right, draw the non-aromatic intermediate in the electrophilic aromatic substitution reaction below. There are multiple resonance structures for this intermediate. Draw any of them that you want. I'm going to draw the active electrophile here just because it's going to give us a little bit of a place to push arrows to explain how it can form. So when you put iron trichloride together with chlorine, you get this intermediate. And this aromatic ring is going to want to attack it. It attacks here because this part is a really good leaving group. So then the thing you need to know is where does it attack on the ring? And we've got this species, which is an orthopara-director. So it wants the reaction to happen there and there. And then this thing right over here, this is a meta-director. So it wants the reaction to happen here and here. So this is a ring that's doubly activated for the substitution happening in those two spots, and they're identical because the molecule has this mirror plane of symmetry that goes through it. So the chlorine will either end up here or there. It's the same thing. So a pair of electrons can come out, attack that chlorine, and then you get, as one of the several possible resonance structures, our OH group here. This group is still there. The ketone is still there. That double bond and that double bond didn't participate, but now we've got a chlorine in this spot. There's a formal plus charge there, and I'll draw the hydrogen in here just for completeness because that was there originally and it hasn't left yet. That's what happens in the last step of the mechanism is weak base comes by, plucks that off, and then you restore the aromatic ring. Okay, can we get 4 reactions done in 2 minutes? 1 minute? I think we can. Put 1 minute on the clock, please. This is an orthopara-director. So this is an orthopara-director. You can find that in the list. This is another resource that you have, is that list of activating and deactivating groups and their directing effects. If you're going to get one thing out, the para position is the least hindered. So you're going to want to put the acyl group there, which is B. Then you reduce the acyl group with this Clemmensen reduction. That reduces the acyl group to an alkane, that's A. This is Friedel-Crafts alkylation, but it is on a group that undergoes a rearrangement. So you hook the aluminum to that chlorine, generates some cation character there, and then a hydride shift happens and you get the cation in that position. So you put an isopropyl group on the ring. So this is going to be C. And then that gets oxidized because it has a benzylic hydrogen, and that leads to carboxylic acid there. That's D. So that's probably all the time we have, but that gets you through almost all of the exam. That is, yeah, there's basically 2 questions left after that. And it's the stuff we just, a lot of the stuff we talked about. So recently. Best wishes when I see you on Friday. Have a good day. Drive safe in the snow.